Hello guys, this is Nihal and let us solve 7th B question of BPSC 64th BPSC Mathematics Optional Paper 2019. So it says that if U is an ideal of a ring R, then show that R mod U is a ring and is a homomorphic image of R. So this question is from abstract algebra. In fact, it is an easy question, but little lengthy question. So let us solve this question. Mm, Given that U is an ideal. So first of all, we need to know that what is ideal of a ring R. Ring R. So ideal is a subring which satisfies the property that if U belongs to U and R belongs to ring R, then the composition UR will be inside U. That means let us assume that this is ideal U and this is ring R. So if we multiply an element of U with a element of ring R, that is small r and small u, then UR will be inside U. That means it will consume all the multiplication of elements of U and R. This is the ideal U. So this question asks us to prove that R mod U is a ring. So first of all, we need to define what is R mod U and what are the those two composition which we need to define on a ring R mod U. So R mod U is equal to cosets of the form R plus U, where R belongs to ring R. So over the composition of 2 plus and multiplication, which is defined as, let us say, A plus U and B plus U, two elements of R mod U. Then we will define composition A plus U plus B plus U as A plus B plus U. This is composition 1, and multiplication is defined as A plus U multiplication B plus U is equal to AB plus U. This is 2. So to prove that R mod U is a ring, we defined what is R mod U, and the two composition is defined as these equation 1 and 2. Now first of all, we need to prove that these two are well defined operations, and then we will move further. So to prove something is well defined, we need to prove that if x is equal to y, then fx has to be equal to fy. So that means let us assume that a plus u is equal to a dash plus u and b plus u is equal to b dash plus u. So to prove that these two operations are well defined, then we have to prove that a plus u plus b plus u is equal to a dash plus u and plus b dash plus u. That is, a plus b plus u is equal to a dash plus b dash plus u. This we need to prove. Also for the second composition, we need to prove that ab plus u is equal to a dash b dash plus u. Let us prove these two. So we know that a belongs to a plus u. Why? Because 0 belongs to U because U is an ideal and also a subring, so it is property of a subring that 0 belongs to U, or this you separately can prove that a subring contains 0. So, so how A plus 0 belongs to A plus U? That means A belongs to A plus U. And A plus U is equal to A dash plus U that we have assumed. That means A belongs to A dash plus U. So A is equal to A dash plus some U1, where U1 belongs to capital U. Hence, similarly, B can be written as B dash plus U2, where U2 belongs to capital U. Now let us find A plus B plus U is equal to, sorry, let us find A plus B is equal to A dash plus U1 and plus B dash plus U2, which can be written as A dash plus B dash plus U1 plus U2. That implies, let us take A dash plus B dash to the left hand side. So A plus B minus A dash plus B dash is equal to U1 plus U2. We know that U1 and U2 both belongs to capital U, so their addition also will belong to capital U because U is an ideal and ideal is closed under addition. So belongs to capital U. That means A plus B minus A dash plus B dash belongs to capital U, which implies that A plus B plus U is equal to A dash plus B dash plus U. Why this happens? Because we know that if X minus Y belongs to H, if and only if X plus H is equal to Y plus H. So this first part is proved. So let us prove that this second composition is also closed. We need to prove that AB plus U is equal to A dash B dash plus U. So what we need to prove that AB minus A dash B dash belongs to U. So how we prove this? A is equal to A plus U1, A dash plus U1, and B is equal to B dash plus U2. So let us multiply these. AB is equal to A dash plus U1 multiplied by B dash plus U2. This can be written as A dash B dash plus U1 B dash plus A dash U2 plus U1 U2. Now we know that U1 U2 will belongs to capital U, and since U is an ideal, so A dash multiplied by U2 will belongs to capital U, because A dash is element of a ring and U2 is element of this ideal, so their product will belong to ideal, and this also will belong to ideal. So this can be written as, so AB minus A dash B dash, this can be taken to left hand side, is equal to something which all belongs to U. So this belongs to U. That means AB plus U is equal to A dash B dash plus U. Hence we prove that second composition is also well defined. Now we need to prove that this R mod U is a ring. So for ring, we need to prove that with respect to plus, it is a commutative group, commutative group, and with respect to multiplication, it is closed and associative, and also it satisfies the distributive property of A plus B into C is equal to AC plus BC. So for the plus operation, we need to prove that this is commutative group. So let us assume that A plus U and B plus U are elements of R mod U. So A plus U plus B plus U is equal to A plus B plus U. From the first composition we have defined like this, and this element is of the form x plus u of R mod u. That means this belongs to R mod u. That means under plus sign, under it is closed. So, and let us prove that this has an identity. Let us assume that 0 plus u is an identity. So a plus u and plus 0 plus u is equal to a plus 0 and plus u, and 0 is identity of R, so it is equal to a plus u. So it has an identity. Let us prove that it is associative. For associative, a plus u plus b plus u bracket plus c plus u is equal to, let us operate first within the bracket, so it will be a plus b plus u and plus c plus u, which is equal to a plus b plus c plus u, which can be written as, since A, B, and C are elements of ring R, and R is associative with respect to addition, so it is A plus B plus C and plus U. So from the addition of first composition, this can be written separately, A plus U and plus B plus C plus U. So it is a ring. It is associative with respect to addition. For inverse of A plus U, let us assume that minus A plus u is inverse of a plus u. So a plus u plus minus a plus u is equal to a minus a. From the first composition, as we have defined, we can combine these two, is equal to, this becomes 0, 0 plus u, which is identity. That means uh, if you operate a plus u with minus a plus u, we get identity. That means minus a plus u is inverse of u. That means every element has inverse with respect to addition. For commutative, let us assume that a plus u plus b plus u, and by definition of addition, as we defined in the equation 1, a plus b plus u, and since R is itself a ring and A and B are element of ring R, and R is that means R is commutative with respect to addition, so this is B plus A plus U, and this can be written as B plus U plus A plus U. That means it is commutative group with respect to addition. Now we need to prove that with respect to multiplication, R mod U is closed and associative. So let us assume that A plus U is multiplied with B plus U, and as we have defined in composition 2, it is can be written as AB plus U, which belongs to R mod U. That means it is closed. Now we need to prove that it is associative also. For that we need three elements of R mod U, that is A plus U multiplied with B plus U into C plus U, which is equal to, let us operate first within the bracket, so A plus U multiplied with BC plus U, which is equal to ABC plus U. So this can be written as ABC plus U, which is equal to AB plus U and multiplied with C plus U. This also can be written as A plus U multiplied with B plus U and C plus U. That means it is associative with respect to multiplication. Let us prove that these two compositions are distributive. Distributive means A plus B multiplied with C is equal to AC plus BC. So elements of R mod U is of the form A plus U, B plus U, and multiplied with C plus U, which is equal to, let us first operate within the bracket, so that will be A plus B plus U multiplied with C plus U. So by the definition of multiplication, this C will be multiplied by A plus B, which is equal to A plus B into C plus U, which is equal to AC plus BC plus U. Since A, B, and C are elements of ring, and ring is elements of ring is satisfy distribution property with respect to addition and multiplication. So we can write like this. This is equal to AC plus U plus BC plus U. That is what we wanted to prove. This shows that R mod U is a ring. Now we need to prove the next part of the question, which says that R mod U is a homomorphic image of R. So how to prove that R mod U is a homomorphic image of R, for which we need to define a function from R to R mod U, and need to show that this is an image of R and F is a homomorphism. So let us prove this. Let us first of all define what is F. So let us define F. R is equal to R plus U. So R plus U belongs to this R mod U. So first of all, we need to prove that this function is well defined. Guys, you need to give some attention to this uh, catch, that whenever you define some homomorphism or isomorphism or a new function in the exam, you need to first prove that this is well defined. Otherwise, there is no meaning of defining without proving that this is well defined. So to prove well defined, let us how we prove well defined is that we take two elements as equal, and we prove that their image is also equal. So that means equal elements do not have different images. Function is defined as that element A has a unique image in codomain. Codomain. So if A has two images in codomain, that means it is not well defined. So let us assume that A is equal to B. So A plus A minus B is equal to 0. 0 belongs to U. That means A minus B plus U is, sorry, if A minus B belongs to U, that means A plus U is equal to B plus U, which is FA is equal to FB. That means F is well defined. Now we need to prove that F is homomorphism. And for a function to be the homomorphism over a ring, means it has to satisfy two property. FAB is equal to FA multiplied with FB, and FA plus B is equal to FA plus FB. So let us prove that F is an homomorphism. So let us assume that A and B belongs to ring R. So F A is equal to A plus U, F B is equal to B plus U. So F of AB is equal to AB plus U. And how we defined composition with respect to multiplication is that this can be written as A plus U multiplied with B plus U. That means this is A plus U is image of FA, and this is image of FB. So FAB can be written as FA multiplied by FB. So we proved first part. Now we let us prove second part, that is A plus B ka image. So FA plus B is equal to a plus b plus u. That is how we define the function. And this can be written as a plus u plus b plus u. That is how defined plus composition. So this is image of fa, this is image of a, and this is image of b. So is equal fa plus b is equal to fa plus fb. We proved second part. That means it is a f is a homomorphism. So question asks us to prove that R mod U is a homomorphic image of R. That means we also need to prove that this homomorphism is onto. So to prove onto, let us assume that any element R plus U belongs to R mod U. And if we are able to find a pre-image for this element in ring R, then it is proved that it is onto. So the obvious choice is R. So for every R plus U, there will be an R in capital R, that is ring R. So such that fr is equal to r plus u. That means we are able to find a pre-image r for every element r plus u of r mod u. That means it is onto also. Hence, we have proved that r mod u is a homomorphic image of r. Thank you guys. You can join Telegram group for discussion, and also you can ask your doubts there. I will be happy to solve your doubts. Thank you.